So my name is Roman Yelzarov. I'm CTO at Devexperts and the original architect of ThinkoSim trading platform, which is now owned by TD Ameritrade. I'll tell you a market data story today. So Devexperts was founded in 2002. That was actually 10 years before fintech was even a word. As you see in this Google Trends, like it really caught up in 2013, something like this. So we founded with a mission to provide high technology for the financial industry. And since then, we had lots of great customers from equity brokers, forex dealers, exchanges, market makers, lots of cool projects, lots of interesting connections. Our original vision did not in any way include us becoming a market data vendor. So we thought, kind of, this is a solved problem, so we just, in all the systems, we just took market data from third-party data vendors, wrote gateways to process their data, then distributed to our customers. We solved what I call, last mile of data distribution problem. By 2008, we already had a platform that could serve 100,000 online customers from relatively modest, rack of hardware. So, and it's every customer had its dynamic subscription, so you just type in a code in a watch list and you get immediately an answer. So this kind of was solved problem, third-party data vendors just fed us the data from exchanges. That's 2008. But of course, when we providers for technology for our customers, when code stopped ticket, they were blaming us, that something went wrong. And most of them, the culprit was somewhere upstream, some software network problem. And we can understand that. At that time, especially 2008, the data rates were growing exponentially. Option trading was catching up like a firestorm. More exchanges, more trades, more quotes, everything, more symbols, trade options. It just grew. Around 2008, you see the option price reporting authority data rate has reached 1 million messages per second, has surpassed them, and started to go up into tens of millions category. It was really huge. And what the data vendors offered us as a solution for the market data, add more hardware. Every year we're adding more and more hardware just to serve the same number of customers we had at our front end. It increased maintenance cost and decreased system reliability. We ended up with this really bizarre situation because in reality, we had all the technology there to handle all the market data. We had these racks of vendor hardware that was feeding us market data just to put it into one multiplexing server on our side and then stream it to the network edge where it gets distributed to customer. And it's all scalable, so like each edge server handles 5,000 customers, so one rack handles 100,000 of them. So we had all the technology to market data better, and that's all we needed is to become a market data vendor. And in 2008, we actually made this decision. We are becoming a market data vendor. So we have to register as a vendor. We'll write all the connections to exchange ourselves and be done with it. So that's how dxFeed was born, which is short for Devexperts feed. So we quickly rolled out the solution, created two redundant data servers in Chicago, New York, started serving all our customers with our own market data through the distribution pipes that we already had. And the real test for our technology really came in 2010. That's when on May 6, 2010, the flash crash happened. It's a unique event where the liquidity market just disappeared for a few minutes and reappeared again in a few minutes after that. It was like a really huge stress for all the systems. Like you had huge spikes in market data. Some stocks at that time traded, like Accenture traded in 1 cent during that time. And Barron's Magazine even ran a special article about that. And they, because they review all the retail trading platforms, they quickly checked how different retail platforms are feeling, and they wrote, that the only trading platform that was usable at the time of flash crash was Thinkorswim, that was using dxFeed data and was based on Devexperts market data technology. And of course, we were very proud of ourselves. That was proof that we're on the right track. So what else could we do? What was just a start for us? We decided to go into historical market data. But of course, everybody else does store historical market data. So it's what you can invent there. It's a big but a manageable amount of data, I can see. As a good yardstick, consider this. If you ever look at the US option quotes data rates, that's the largest source of quotes in the world. That's, if you take around 1 million messages per second, multiply by 6.5 hours of a trading day, and multiply by 43 bytes, that's the standard size of quote packet in the Opera, you get almost 1 terabyte of data. It's like really close equality here. That's a good yardstick. That gives you kind of a scale. Like if you have 3 messages per second, that's 3 terabytes of data. So you can measure it. And of course, there is nothing exceedingly large about it. There are out-of-the-box storage solutions that can store this kind of data. If you store it if you do this terabyte per day for a few years, you get a petabyte of data. It's still manageable. Especially if you write it to a log, where you just record every event, you don't even need a very high throughput hardware. I mean, just a big cluster of it will solve it. So now you have stored though. Just get some storage solution. So what you're going to do with this data? You're going to run some queries on top of it, asking some questions like, what were the trades of this particular symbol, this particular time range, things like that. How do you answer those queries quickly? Even if you're asking for data from 1 day, that means scanning a terabyte of data. Of course, sharding or splitting your data helps, so you can build this massively distributed system, split the data in small pieces, so you can run your query in parallel and get the answer quickly. Lots of hardware. But we even had a bolder goal than just that. Our goal was to build a market data time machine. We wanted a system where you can go back in time in our trading application and just open the market at any time in the past and see what's going on. Like a DVR that records all the shows that are on air simultaneously and then lets you come back in time and see any subset of those shows, what was going on. So that was our goal. So that's, of course, you can use existing big data solutions. And by some chuckles here, I see some of you may have, worked with those in the past, and you'll see these kind of images typically on developers conferences where developers between themselves, discuss big data, existing big data solutions like Hadoop and how they work with this, stuff like that. And what's big data? Big data is about crunching lots of data, crunching it, processing. That's where you need the scale, and these huge clusters. In our world, all we need is really simple questions. Like our customers, brokers, they use the data for what? They use it for compliance and for visualizations like charts. They typically query one symbol at a time. They don't need to process this data to mine it or stuff like that. They actually need simple things. So we came another way. So we used the solution that actually powers our market data distribution. That's compression. The idea is relatively simple. If you look at market data as it typically flows through the network, you start noticing various patterns. For example, you see that in many exchange protocols, for example, the size occupies 4 bytes. But your trader quote size is usually small. If you use variable length in cutting scheme, that you can feed it into one byte. Then you start looking into other fields and find similar patterns, you can save here and there, and relatively easy, you can get your opera code that was 43 bytes to 20 bytes and less. Then you implement, make an efficient implementation of it, and you go. It's actually a pretty well-known technique. It's used in many solutions, nothing groundbreaking about it. Exchanges still don't use it. It's not widely used by exchanges, which is probably good, because it's when you have a plain, fixed message size protocol, it's easy to document, easy to support, and frankly, exchanges don't have this problem, like serving 100,000 online customers, right? It's our vendor's problem to do it, not the problem for exchange. So we've implemented this all in open source, so we can provide both code and services to our enterprise customers. But unfortunately, just compressing individual events does not solve the storage problem, because, okay, you can reduce the size 3, maybe 4-fold. It's not a big qualitative difference. It doesn't change the world. So in order to really make a difference, we needed something better. And that's the answer we found in delta compression. So that is simple. So first, we take the log of all market data events, like all codes from different symbols are mixed between each other. Then we arrange those into blocks where codes from different symbols come together. And then we look at neighboring code and we start finding patterns, like prices are similar, quota sizes are similar, times are similar. There are lots of patterns. It's very similar to how columnar databases operate, if you're familiar with those. The difference, though, the columnar databases operate in columns. And we look at the event as a whole, because when you retrieve the data from market data storage, you don't need just size column of your market. You need the code as a whole, trade as a whole that was stored. So we analyze the events as a whole and compress the delta between neighboring events. And that gives some radical results. And especially if you use another technique of compressing symbols, like look at the option symbols. That's some symbols for IBM options. They're all repetitive and very normally formed. So if a quote doesn't trade often, like an out-of-the-money quote, even the symbol starts occupying a lot of space. There are no quotes. So we've by exploiting this regularity, we were able to compress the symbol dictionary in such a way that on average, every symbol takes less than 1 bit here. So all this combined in our latest versions of our compression technology, we were able to shrink the data a factor of 10 to 50 depending on the source. And that makes it a big difference. Your 1 terabyte file for a day now becomes just a few hundred gigabytes. And actually a few dozen gigabytes. You can feed it all into memory. And that makes it different because memory is fast. And you can feed the memory in one machine. You can query quickly. If people want just the data from last day, you can, it's all in memory, it's up there. And that's what people usually look at. They look at the data from the last day. So our original market data solution was based on processing. So we pre-stage the log files for a day, then we compress them for a day, upload it to long-term storage, so that way you can query the data at T+2. That was still great. We use it for education, so you can showcase your trading platforms through the weekends when there are no live codes. You can go back in time, turn it on, and see what was going in the market. In the recent release that we rolled out in 2015, we've implemented delta compression right on the exchange boxes. So the data is delta compressed right there, so you can query it immediately. And it is kept in memory of those servers. So a short demo here is this. We just make a call to our server. Sorry, it's on the wrong screen. So we just make a call to the server, and you get stream of events for all the Google quotes for a minute. You can go to URL, change the symbol, type something else, IBM different time frame. It's all works instantaneously because it's all kept in memory. And it's all served from relatively modest hardware footprint. There's no racks on record servers or anything like that. So that's all. That's just a small fraction of what we do at Devexperts. Thank you for your attention. If you want to know more, come to our booth. Thank you.